Greetings to everyone down in Argentina. This is Tom Rockwell, and at Carlos's request, I'm going to provide an overview on the paleoseismic work we have done along the Precordillera north and south of San Juan. And of course, Carlos has been heavily involved with this work, as has my student Danielle Ragona and Professor Andrew Meigs from Oregon. So I want to thank Carlos for inviting me to give this talk. Some of this work is published, and the rest of it, Carlos and I are working on now to see it to publication this coming year. So the three sites I will talk about, the three study areas are La Laja, which of course ruptured in 1944, and that's to the north of San Juan, and then two sites to the south, Marquesado and Rinconada. And one of the questions that we have is the low topography that we have near San Juan a consequence of this being a resilient segment boundary, or do we see evidence of ruptures that might have gone through there? Do we see clustering of earthquakes between La Laja and those to the south? So these are some of the questions we'd like to address with paleoseismology by dating past earthquakes on these different segments. This area is well known for its earthquakes, as you all know. There have been a number of relatively large earthquakes, including the magnitude 6.7 1944 earthquake, the San Juan earthquake, and then a 7.4 under Pie de Palo in 1977. And there's been a slew of these magnitude 5 earthquakes, which when you put them into cross-section, this is a section from Andrew Meigs, this would be the main shock rupture for the 1977 earthquake, the 7.4, and then this is the interpreted causal fault over here under the Eastern Precordillera for the 1944 event. And according to this model, the causative fault for 1944 is a blind thrust, or largely blind. It looks like it has a back thrust that comes up under the Sierra de Villacombe, and the 1944 rupture itself is interpreted as a bedding plane fault. So this is a detail of that. The Sierra de Villacombe fault is not active, and so the expression of faulting is limited to the La Laja and related bedding plane faults. So we'll talk a little more about that, because I think one of the questions is, is the depth of the blind thrust, and I think that's it's been modeled, but it's really not that well resolved. Okay, so this is a map of the La Laja area, and it shows a number of older terraces that are progressively higher or progressively older. So there's been long-term uplift of the terrain here. It also shows several bedding plane faults that are to the northwest of the La Laja fault. The La Laja fault's down here in the southeastern corner. And none of these other faults ruptured in 1944. It was just the La Laja fault. So this is a nice overview. This is a view looking to the south towards San Juan. This is the frontal, fold. The axial surface of the fold is out here in the alluvium. And then this is, of course, off to the left is the basin that's forming as a result of this folding. And you can nicely see the uplifted terraces that are in the footwall of the La Laja fault and the hanging wall of the Sierra de Villacombe fault. So the site, I'll show you several trenches or results from several trenches, but first one I'll show is we trenched the 1944 rupture up on what was mapped as the T2 surface, as shown here in red, or above it. Here, and then I will show a large exposure. We dug a trench right at the front of the fold, basically exposing the QT3 terrace surface into the subsurface. So we'll talk more about that in a few minutes. The 1944 earthquake in modern alluvium, this is the channel, the active channel just to the north of our main trench on the La Laja rupture. And we documented about 40 centimeters of dip slip in this particular trench based on this offset of gravel. There may be some off-fault warping here. The measured slip from 1944 was about 40 to 50 centimeters. And we have about 50 centimeters in the trench that was in the older alluvium above this. So this was one of our first trenches across the 1944 rupture. We excavated a trench up on the T2 surface. This is Daniel Ragona staring the fault in the face here. So it was very, very nicely exposed with the tertiary bedrock being thrust over alluvium. And as I'll show you, there's a number of cluvial wedges here. So you can see the coarser finding up and then coarse again finding up. And we see this repeatedly in this section. So this was logged in detail. And I'll show you a detail of the log in a minute. And then to get an idea of displacement per event, we reconstructed these event by event, stripping back first the 1944 earthquake and then subsequent or previous earthquakes prior to that. So these cluvial wedges were generally represented by these funny upward sequences where we have gravel and then gravel with matrix. This represents the collapse of the nose of the fault, and it finds upward. And then each of these cluvial wedges is capped by a soil that has gypsum in it. So you can see the gypsum, this white stuff that's developed in the top of this package here, and then it was subsequently refaulted and had more material on top of it. So we identified evidence for 9 earthquakes in this section, and as I'll show you, they get progressively older as expected based on the dating, but we used optically stimulated luminescence dating to date the earthquakes. So here are some of the age control. The dates ranged from about 2000 back to almost 45,000 years in age for the different cluvial wedges. And I will show you in a couple minutes the context of these and that we use to date the individual events. But before I do that, I want to show you the reconstructions because we use these to estimate displacement per event for the last 9 earthquakes that ruptured the La Laja Fault. And of course, for E1, this is 1944. It was about 50 centimeters measured here. And so we remove 1944, and this is what it looks like. And then we sequentially removed previous events. So event E2 had more displacement, about 73 centimeters. E3, about 89 centimeters. E4, 71 centimeters. E5, 42 centimeters. E6 was 58 centimeters. E7, 79 centimeters. E8, 60. And E9, 64 centimeters. So in each of these cases, we're stripping back the alluvium that was deposited after the event, including the cluvial wedge, and restoring the paleosurface as it was before each event. So in the end, we have about 586 centimeters total represented here for slip, direct slip on the fault, which is interesting because that's just reconstructing the scarp. But at the same time, we're growing the fold. We're growing the overall scarp. And that has about 10 meters of total when you look at offset of the T2 surface. So in this particular slide, we're looking at the reconstructed slip per event. So we total about 586 cumulative centimeters. The total estimated based on we're looking at about half the displacement, about 55% is represented by the brittle slip. So this is our estimates of the actual total slip per event on for each of these earthquakes. And from this, 1944 was relatively small. There were some of these events that produced nearly 1.5 meters of overall deformation or displacement across the La Laja Fault. And so the average displacement is over 1 meter. As measured in a trench, it's about 65 centimeters. The other thing is, here's the dates that we come up with based on the luminescence ages. 1944, of course, is known. The penultimate event was about 3,000 years ago. The pre-penultimate was about 8,500 years ago. Events 4 and 5 are poorly dated, so we didn't have good age control on those. And then events 6 and 7 are about 20 and 23,000, and event 9 is about 31 to 32,000 years. So that yields an average recurrence interval of about 4,000 years. And as you can see, there's some variability. It's 3,000 between 1944 and the penultimate, and more than 5,000 between the penultimate and the pre-penultimate event. So there's some flexibility in the recurrence interval. It's about 4 plus or minus 1,000 years. So this is what it looks like through time. The vertical bars are estimated total slip per event. And then the horizontal bars are the ages of the events as we know them with their uncertainties. And so events 4 and 5 are poorly dated, event 8 is poorly dated, but the others are fairly well dated. And this appears to be fairly characteristic and periodic within bounds. So that's good news for San Juan, at least to the north of San Juan, because the likelihood of 1944 occurring again is very, very low. But what about to the south? We'll be going there in a few minutes. First, I want to show you some of the other work we did there. At the fold front, we excavated a very large trench that went down about 6 meters. This is an excavator for scale. And we were interested in looking at the axial surface migration over time. And the idea being that we should see clear evidence of these units in the trench being rotated less and less as we get to the modern alluvium. So the modern alluvium is at the surface here, and it's undeformed. And then you get progressively steeper tilt as you get to the east. So going 12 and up to 22, 24 degrees, maybe a little less here. So this is one face of the trench. This is the other. So we're trying to estimate this or determine the rate of migration of the axial surface. And I want to point out one feature here. This, if you can see my arrow here, it right below the 12-degree mark, there is a fault, and that fault breaks almost to the surface. It didn't break up into the modern alluvium, but it breaks everything below it. And one of the questions here is this an out of syncline fault, or is this the tip of the thrust? So that was a question. The interpretation right now is it's basically an out of the syncline fault that results from being squeezed by the folding, so very close to the axial surface. So based on the model, Andrew's model, he's basically modeling this axial surface deformation through this folded Holocene sediment. And this results in about 28 meters of inferred displacement if this represents slip on the fault at depth. This represents 28 meters that occurred after the incision into the T2 surface, and of course involves the T3 and T4 deposits. So we know that the T2 surface is about 32,000 years in age. So it gives a minimum slip rate of about 0.9 millimeters per year if correctly modeled. One interesting aspect of the 1944 rupture trace is that there were many areas that had ponded silt behind. And we saw this in Baja California in the 2010 earthquake. It produced a lot of rock falls in the mountains and a huge amount of dust, and that dust washed down and was ponded behind the uphill facing scarp in 2010. So we think the La Laja Fall is doing very much the same thing, the earthquake produced rock falls that produce dust, and that dust accumulates behind the fault scarp. And here we were actually hoping, because we're going to trench this here, we're hoping to find past dust accumulations that we could date with OSL. So here we are trenching it. The dust I was just showing you is just to the left of Danielle Ragona. I believe that's Carlos over there to the right. And this is one of the trenches that we excavated across the 44 trace. And here is that fine sandy silt ponded alluvium that ponds behind the fault scarp produced in 1944. So it's only about 10 centimeters thick, but it was very distinct. This is the upper panels, the actual photomosaic and trench log. It includes the 1944 earthquake. And you can see there's other units like Unit 6 and Unit 8, which are fine-grained units. And it turns out those pond behind the fault as well. 6 through 8 represent a sequence of fine alluvium that behind the fault scarp that was produced during, that produced also the cluvial wedge 2. So this is a reconstruction of, or this shows what the trench looks like now in the middle panel, with Unit 1 being the ponded alluvium. And then the lower panel is removing the effects of the 1944 earthquake. And when you do that, you can see that there was a cluvial wedge produced by the penultimate earthquake, and ponded behind it was a lot of alluvium. And it's much more alluvium than we have ponded by the 1944 earthquake. And remember, the penultimate earthquake was much larger, had much more displacement than the 1944 earthquake. So it's presumably much larger. The timing of that earthquake from this trench, or from actually an adjacent trench that had charcoal in it, the charcoal dated to around, see, radiocarbon dates around 2.8 to 2.9 thousand years. Those calibrate to around 3.2 thousand years. And we're in the alluvium that immediately postdated the earthquake. So this would suggest that the penultimate earthquake was around 3 or 3.2 thousand. That's the same age we get for the penultimate event in the trench 1 that I showed previously. Okay, so next we're going to go down to Rinconada, this area south of San Juan. San Juan's this bullseye right here. And we're going to look at a sequence where you have, again, bedding parallel faults that verge to the west, and therefore coming off the slope of the mountains are going to pond alluvium. So we're going to have these fine-grained ponded alluvial events again. This is a Google Earth image. I think you can see very nicely the bedding is shown here. And these are the fault scarps. You can see the fault scarps very clearly cutting the alluvium. There's this wedge that's uplifted here. It's the fold front. So this is the eastern front of the fold. And then behind it is, to the west, is the bedding plane fault, analogous to what we saw at La Laja. So again, this is the general model. We don't have the Sierra Vigicum fault at the surface, but we have these bedding plane faults that were activated. Okay, so one of the first things we do is we map out the quaternary deposits. This is Andrew's mapping. He was mapping while I was trenching. And the area that we're working in is up here in the upper left. And there's some, this is one of the fault scarps, just almost to the edge of the paper here, or the mapping. This is what it looks like, again, in Google Earth or from the air. And one thing to point out here are all the beautiful terraces that are representing the long-term uplift. They're recording the long-term uplift, this block between the fold front and these bedding plane back thrusts. This area wouldn't be a great place to trench because you're not ponding any alluvium, so you probably don't have much of a rupture history, but there are other areas that do. So we chose an area right next to the road here, right just on the south side of the road. There's a beautiful area of ponded alluvium, and we sunk 2 trenches across the fault in that area. I do want to point out this apparent left deflection in this channel. That might indicate that there's a left lateral component to the Rinconada fault system in this area. Okay, so here we are at the trench sites. We excavated 4 trenches, T1 and T4 were on the western splay of the fault, and T2 and T3 are on the eastern splay of the fault. And so we have paleoseismic information from both of those splays. So, of course, here we are opening trench. One thing I haven't mentioned is what we commonly used to do is grid up the trench face, photograph it, and then construct photo mosaics on which we logged. And we also made paper logs in the field. So each of these 1 meter by ½ meter panels would be photographed. When we go back to the hotel, we'd mosaic them together, print out the mosaic, and then log on it. And on the right panel here, you can see the low angle fault coming up. And then this actually has a little back thrust shear that comes up almost to the surface. I'll show the log for that in a minute. Right here. So here's this low angle fault. This right at the back of the trench, it increased in dip to more or less parallel to the tertiary section. But this fault came up and went flat, which means it was rupturing up to the surface and overrode the surface at the time. So we interpret this to have been an actual surface rupture. What's really interesting is that because this pond had this fairly thick section, 2.5 meters or so of alluvium that accrued, subsequent events, one of them back thrust along this this fault here, and the most recent event is completely blind. The most recent event is represented by that yellow line, shown as E1. E2 is the purple line, and E3 is the orange line. And E1 is completely a blind event. And I'll show you that. You're going to say, well, are you sure that's an earthquake? And I'll show you, yes, because we did another trench right along a channel that was defeated by that particular event, E1. So at this particular trench site, this is the western trench. We estimated the event E1 at about 2.6 thousand years and event 2 at about 7.15 thousand years. This is based on radiocarbon dating of charcoal. We had plenty of charcoal in this trench. And then our event 3 was older than 7.3 thousand. This is Andrew's model for reconstructing the slip per event in this particular trench based on the trench logs. I'm not going to go into this, but we had evidence for 3 events in the past 8 to 10,000 years. Okay, so what about the eastern strand? Eastern strand had very similar stratigraphy with this capping alluvium and over this fine-grained ponded silt deposits. And then the thrust was beautifully exposed here, bringing tertiary over the alluvium of unit 300. And again, we had quite a few radiocarbon dates and OSL dates. So we developed an excellent chronology for this particular site. And oops. So, and this is Andrew's reconstruction for the tree 3, showing again the 7, very similar to what we had in T1. Now, when I mentioned that this deformed, this last earthquake, E1, had basically blind deformation. We know this from evidence from T2. And this is we dug this in a channel that looked like it was defeated. So the channel flow direction is from left to right. And that's unit 100. And it actually has to go uphill by about 30 centimeters to get over the fault. This is unequivocally deformed because the original flow direction was from left to right, and now it's stuck by this deformation. So the fault did not rupture through unit 100, but there's no question that unit 100 was folded in this most recent event. One nice thing too here is there's a lower strand of the fault. I didn't point that out in the other wall, or the other trench, but this is then capped by some alluvium. And we've interpreted this as an axial surface. You can see my cursor, but it's well pointed out by the arrow that says axial surface. So we have this cluvial wedge from E3. We've interpreted a folding event for E2, and then another folding event for E1. So the last two earthquakes in the eastern strand were blind events, even though the pre-penultimate was a surface rupture. So this is very interesting. I've not seen this elsewhere, where you went from surface rupturing to blind. Normally, once it reaches the surface, it stays at the surface and ruptures through. And perhaps that's because these are smaller events, we're not sure. But nevertheless, the deformation from these events is recorded in folding at the surface and in the subsurface. So here are many of the radiocarbon dates. These are that were collected from T1 and T3, and that record this early to mid Holocene event. It's very well dated at 7.15 thousand calibrated years. These are the raw radiocarbon dates, and they're going to be older when they're calibrated. All right, so here's our summary of Rinconada. Evidence for 3 events, one at around 2.8 thousand, one at a little over 7,000, and one that's older than 7,000. And I'm not sure we ever got OSL 13 dated. I'm going to have to check on that, because if we do, then we can constrain the age of E3 as well. Okay, the last site I will show is Marquesado, which is right next to San Juan. It's just south of the city, and it's again along one of these east side up bedding plane back thrusts. And these are very evident. In fact, okay, so here's San Juan here, the city of San Juan, and we're on the south side of the San Juan River. Maybe a better name would have been Rivadavia, but because Marquesado seems to be north of the river, but we're south of the river. And note the location of this white spot, because the next slide I'll show you, you'll see part of that in there, and you'll see the fault scarps very clearly. And the fault is going right through that white spot. So here it is, there's the fault, very, very obvious uphill facing fault. And you can also see a secondary, another fault scarp farther up the fan. We only trenched the main scarp in this particular site. And mainly because it had ponded alluvium. So these two little blue spots here are the trenches just south of this road. And it's one of the few areas where we are ponding sediment behind the fault scarp. So this is what it looks like. Very similar to the other sites that had similar stratigraphic context. The fault is the contact between the overriding gravel. This is the alluvial fan alluvium that's late Pleistocene in age, and it's being faulted over this Holocene section. And you can see the gravel again at the very bottom. So we had decent stratigraphy. This is the T1, the north face of T1. And this is one that Carlos and I are debating and working on now. The question for the most recent event is, where exactly is event horizon? In some cases, it looks like this unit 132 is actually faulted and folded, and unit 130 may also be folded here. So this, again, might be one of those situations where it didn't rupture all the way to the surface. It was blind, caused folding right at the surface, which would put the event then between unit 100, this upper strata, which is our interpreted cluvial wedge, and unit 130. The alternative is that the event occurred here between 132, or an event occurred between 132 and 135. And so we're still working out the timing of this particular event. But this is important because either the event is between 5.8 and 7.4 thousand, or it's younger than 5.8. In fact, if this unit 132 is a cluvial wedge, then we probably have another event in here that is mid-Holocene in age. So we also had some beautiful examples of upward terminations. This footwall strand comes up, ruptures up to the orange line, ruptures unit 240, and is capped by unit 220. There's a nice cluvial wedge here from the main strand, but this is great evidence that this is a well-constrained event horizon between 220 and 240. And then we had a third event here that ruptured between, ruptured up through 280, had a nice cluvial wedge cap, which was 270. So it's interpreted to have occurred between 270 and 280. And we see that repeated in each of the other trench faces. Again, the upward termination, maybe, or does it deform the sediment? But this is going to be important in terms of dating the last event. One thing, Carlos, you'll notice we have this yellow line here is faulted. It really probably represents a separate event, and that the youngest event is represented by the cluvium, this gravelly cluvium at the surface. So we'll have a discussion on that later. And then again, an event between 220 and in this case 260, and another between 270 and 280. And we had a fourth event here that was interpreted between 280 and 300, and it produced a nice cluvial wedge. We have a date back here of about almost 18,000 years. I don't think I have that in the compilation that I'll show you, but so we have dated as many as 4, possibly 5 events at this site. Same kind of story with the other trench. In this case, the fault ruptures up to and folds unit 135. Looks like it's maybe capped by 130 and unit 100. And then again, we have down here a evidence for a fourth event or that was on a secondary strand. Okay, and then T2 south face, same thing. It's not clear how high this rupture actually went and whether it was blind, because it clearly folds this contact. And then the question is this a cluvial wedge or is it unit 100? We're now leaning towards thinking that unit 100 is the cluvial wedge. So we had reasonably good age control for this section. However, as many of you may know about luminescence dating, you have the potential of having some grains only partially bleached, and we clearly had that in this case. These are ordered by stratigraphic section, and we have older dates that sit above younger dates. So what that really means is that the older dates have a substantial amount of grains that were only partially bleached, and so what we have to do is use just the youngest dates to constrain the ages of the events. So even though we have 20 luminescence dates, about half of them have too much partial bleach signal to be useful. But that said, here's one interpretation, and again, it depends on where we put this uppermost event, or if it may be in fact 2 events, but they're probably between 100 and 130, but there may also be one between 130 and 135. And then the older events are well constrained between 220 and 240, 270 and 280. And then we had that one that was between 280 and 300. And so in terms of the timing of these, it gets into the question of whether E1, whoops, this got shifted over, but E1 is either less than 5.8 thousand, or if there's 2 events in there, it's the second one would be between 5.8 and 7.4 thousand. We're going to leave that debate for later. But the timing of the MRE is critical to better understand what we're looking at here. And then this should be E2 was 7.4 to 8.7. E3 was 12.4 to 14.9, and E4 was older than 15. It was less than 18,000. So somehow, sorry about that, these all got shifted over. Okay, so when we start looking at comparison between these different sites, we have, of course, 1944 La Laja, Marquesado, which is south of San Juan and south of this topographic low that probably represents a segment boundary. we have 1 or 2 events, and the most recent is either less than 5.8 thousand or between 5.8 and 7.4, versus at Rinconada, it's pretty well dated at around 2.7 or 2.8 thousand. And then we have events at Marquesado that are between 7.4 and 8.7, Rinconada about 7.1 or 2, and versus La Laja, which is around only 3,000. And then for E3 at Rinconada, is older than 7.3, it's not well constrained. At Marquesado, it's 12.4 to 14.9. And then at La Laja is 8.5. And then E4 at La Laja was very poorly dated. So basically that's saying that the penultimate events are not the same age, and that's no surprise since 1944 is so young. So one of the questions then is, if you look at the penultimate at La Laja and you look at the penultimate at Rinconada, they're really indistinguishable in age, about 3,000 years ago. And at Marquesado, we have what likely is an event that's younger than 5.8 and possibly another one that's in between. This is still to be resolved. But we have then an earlier event at La Laja, 8.5, more or less, and one at Marquesado, which is about the same age, and one at Rinconada, which with an uncertainty, because these have large uncertainties, is about the same age again. And then the pre-penultimate at Rinconada is not dated, and unfortunately La Laja is not dated either, so we just have the pre-penultimate at Marquesado. So if this is correct, and if this mid to late Holocene age at Marquesado turns out to be the same, it should be the same as at Rinconada, they're on the same system and not that far apart, then the question is, are we waiting for another event on that on the thrust south of San Juan? 1944, I mean, if you look at the penultimate event, this may represent a cluster. We know that this was a larger event at La Laja, so possibly it ruptured all the way through. The alternative is that this was part of a cluster of events and almost the same age at Rinconada as at La Laja. And does that mean that the system south of La Laja is primed and may have an earthquake in the future? Remember, the recurrence interval is measured on the order of thousands of years, about 4,000 years at La Laja. So it probably is not imminent, but on the other hand, it is something to consider because the thrust system basically underlies San Juan itself. San Juan will be right near the northern tip of this southern segment. Okay, that's it. Thank you very much, and appreciate the opportunity to have presented some of this work, and hopefully you'll see this all in print within the year.